What we're going to look at now is taking functions and doing some combinations of them mathematically. So first we're going to look at the arithmetic on the functions. We're going to add, subtract, multiply, and divide them. It's a very simple concept, very easy to work with. If you have two functions, let's call them f and g. If you want to add them, you just add them. Just straight term by term, like terms. You add like terms. If there are no like terms, then all you can do is write them side by side with a plus sign between them, but you're still adding them. Now, for some reason, I don't see that it saves much writing or space or anything else. The mathematicians decided to write it this way. So be prepared to recognize this way of writing the sum of two functions. Because we have this parenthesis x, you should immediately trigger on the fact that that is a function notation. It is not f plus g multiplied times x. It's actually f plus g of x. That's the way you would say it, is f plus g of x. The literal operation is just a straightforward combination of the two functions. You put a plus sign between them. Subtraction is the same thing, except it's a minus sign. Means the same thing. I mean, it's described the same way. It's a subtraction, not an addition. So that difference mathematically, but you write it in a very similar way. This is f minus g of x. Product, you don't actually put a symbol between them. You use the implied multiplication. Anytime two things are side by side, they're multiplied together. So f times g of x. Division, f divided by g of x. And it's literally just exactly the way it looks. You're just doing that operation. So here are two functions. If you're asked to find f plus g of x, it's literally, I want to take f of x and add g of x to it. Well, f of x is 3x minus 4, and I want to add to that g of x, which is 2x squared minus 1. So if I add those together, I'm going to get 2x squared plus 3x minus 5. You combine any terms that will combine. If no terms combine, then you just write it with a sum between them. But you simplify as much as you can. So nothing complicated about the concept. If you wanted to do division, when you're doing this, if it says the operation with x, then you have to do it with the definitions here. If it says do this, but then evaluate it at a specific value. So this is, I want the division of the two functions, but I only want it at the point where x equals 3. I only want one number out of it. Then there are two ways you can proceed with this type of a calculation. You can either divide the two functions and then plug 3 in for x, or you can plug 3 in for x in the functions and then divide the results. It's usually easier to evaluate the functions at the number and then do the resulting operation with the numbers. Yes? You're given that. It tells you to evaluate there. What it says is, if f and g are defined this way, what's the value of f divided by g at x equals 3? So you're told what that number is. It says so right there. That's part B. Same two functions. Up here we were doing it in general for any value of x. Down here I'm saying I want this one, but only at the value 3. Yes. hmm So probably the way you'd want to do this is you'd want to do f of 3, which is 3 times 3 minus 4, which is 5. And you'd want to do g of 3, which is 2 times 3 squared minus 1, which is 2 times 9 minus 1, which is 17. Then f of 3 divided by g of 3, because remember, this is that's literally all that terminology means. So f of 3 is 5, and g of 3 is 17, so f of g of 3 equals 5 over 17. Now you can do it with x's and then plug in. I could do f over g of x, which would be 3x minus 4 divided by 2x squared minus 1, and then I could evaluate that at 3. It's going to give the same result. You wind up, for this particular case, doing exactly the same things. You're still going to evaluate that function at x equals 3, and you're going to evaluate that function at x equals 3. In this case, it doesn't save much. If it maybe doesn't save anything, but there might be some cases where it will. Point is that if there's a number here, you have a choice. You can do it either way. If that were an x, I have no choice but to do this. So it depends on whether there's an x in the parenthesis or a number in the parenthesis. If it's an x in the parenthesis, you just have to do the brute force thing. So if you have this definition of f and this definition of g, what's f plus g of minus 5 equal to? If you take the number and evaluate f at that value, evaluate g at that value, that's what I've done here. So I evaluate f at minus 5, I evaluate g at minus 5, I get these two numbers. Then what I'm doing is I'm adding those two numbers together. So I add them together here. 44. Same to what's the quotient evaluated at 5, plus 5. Yeah. Okay, so add, subtract, multiply, and divide are very straightforward, very easy, nothing complicated going on. We're going to look at composition now, which gets a little more complicated. The terminology for composition, it still works on two functions, so it's still function terminology. But now, instead of having a plus, minus, times, or divide symbol here, I have this little open circle. It's like a degree symbol, but it's written midway on the line. It's not written up above. It's written in the middle of the line. Same place you would put a plus, but it's a circle. It's not a dot. A dot means multiply. This is an open circle. This is the symbol for composition. What composition means is we're going to have one function work on another function. And there is an order to which this must be evaluated. There is a first function and a second function. What we have to do is we have to evaluate the second function at this argument. Whatever we get from that, we use as the argument to go into this one. Or in other words, we want to get g of f of x. G is a function, f is a function. We work from inside out. We're going to calculate what f of x is. Whatever that gives us, we're going to put that into g and calculate g. If we're asked to get it at x, then f of x is just going to be the expression in x, but then we put that in the location where the argument of g is. So that's what makes it a little complicated. Because this deals with functions, we have to be concerned with domains and ranges. And both g and f have domains and ranges. We're going to evaluate the second function first. So for this way of writing this, g of f, and that's the way it's stated. It's a g of f of x. So you have two ofs in there, g of f of x. Just like g of f of x. So kind of like the opening parentheses represent the words of. So the domain of g of f is all those numbers x which are in the domain of this. So we have to have something that we can solve f for. So it has to be in the domain of f. We have to be able to get an output. If it's undefined somewhere, then that cannot be in the domain of the overall thing. So we have to evaluate this one first. So the domain of the overall thing is the domain of f, but we're going to limit it such that we don't get any values of f which are not in the domain of g. So let's suppose that we had g was 1 over x. And let's suppose that we had f of x equals x. Perfectly valid way to, two perfectly valid functions. If we evaluate this, I can put any value I want to in for x, can't I? Doesn't, because, anything works there. But what happens if I put 0 in here? Then when I plug that result in up here, I'm going to be dividing by 0. So I have to go back and limit the possible values here because it gives me a value of f which I can't use here. That's what this statement is saying, is that the domain cannot be any more than the domain of f. But then you have to look at the result of f and see if you have to restrict that domain further. We'll look at an example. Suppose f is defined as this square root, and that g is defined as that fraction. If you're asked to find f of g of x, that means we evaluate g at x, use that result to plug into here. Which means, remember the variables just are placeholders? So really, this is f of something equals the square root of whatever that something is plus 4. What I'm going to do is I'm going to put something in there. for this particular problem, what I'm going to put is here. I'm going to put g of x there. But g of x is just 2 over x. So f of g of x is going to be the square root of, put 2 over x in there, plus 4. And that's my composition. We don't put x in here, we put the g of x, whatever g of x turns out to be. Well, g of x is just going to be whatever the defining expression is. If this were g of a number, then it would be a number we'd put there. So here's f of g of x. Here is the composition when we write it as f of g. Not valid everywhere though. You have to look at your domain of f. I'm sorry, we're doing g first. We have to look at our domain of g. So if this is g, do we have any limitations on our domain of g? Is there any value of x we can't use? Can't use 0. So the domain of g is minus infinity to 0 union 0 to infinity. It's everything except it's 0, isn't it? So our domain of this overall thing can't be any bigger than that. The domain of this can't have 0 in it either. When I plug that in here, I can get both positive and negative numbers out, can't I? If I put a negative number in, I'm going to get a negative number out. A positive number is going to give me a positive number, right? But when I start plugging those positive and negative numbers into here, because I'm doing this, when I start plugging positive and negative numbers in here, I'm going to wind up with, if I get something that's going to give me too negative a term here, will give me a negative square root, or square root of a negative number, and I can't use that. So we're going to have to look at that. What limitations am I going to have? Well, the limitations are that your square root, what's inside here has to be positive, or greater than or equal to 0. It can be 0 or greater. So we're going to have to limit that. And what does that turn out to be? That turns out to be an inequality to solve. We have to have that. There's our inequality. Actually, it should be greater than or equal to 0. So let's solve that. That's a rational inequality. Make a single fraction out of it. Find the breakpoints. The breakpoints are going to be x equals 0 and whatever that is, which turns out to be x equals negative a half. So here is what it takes to make this work. So what intervals of the number line is that valid in? Well, pick points. So we pick -1 to look in that interval, and it's true there. If we pick in between -1/2 and 0, we pick -1/4, it's false there. And if we pick 1, because we want to be above 0, we can't pick 0. 0 is a breakpoint, so we can't pick 0 for our test. So we have to pick something larger than that. It's true there. So it's true on the two end ones, not true in the middle. Then we test the breakpoints themselves, the 0 and the -1/2. If we let x equal -1/2, the inequality is true, so we're okay there. But we can't use 0 because we already threw it out anyway from the domain of G. And so the domain of the solution throws out everything between -1/2 and 0. Negative 1/2 works. 0 does not work. And when you're working with functions, you do have to be conscious of the domains where they are valid. And especially when you start working with compositions, it becomes somewhat more complicated to figure out where that domain exists. Okay, so using the same two function definitions, previously we calculated f of g of x. Let's calculate g of f of 5. And remember when we were working with adding, subtracting, multiplying, and dividing, I said you could evaluate at the number first and then do the operation? You can do the same thing with composition, and that's probably easier to work with composition. When you have g of f of 5, that means g of f of 5. You can think of the word of as being an opening parenthesis. G of f means g parenthesis f, of 5 means parenthesis 5. And then you close your parentheses. So this is what this terminology says we're supposed to do. Well, this obviously evaluate f at x equals 5. Well, f of 5 is going to be equal to the square root of 5 plus 4 equals square root of 9 equals 3. So this is g of 3. Rather than putting the formula in there, do the calculation and get a number. Put the number then into the second argument rather than that expression. Put the number in. Well, g of 3, though, if I look at this definition, is 2 over 3, and that's my composed function. So do the evaluation of the second function. First function, second function. Evaluate this function at that number. Use that result as an argument of the first function, just as it's shown here. If you write it with the nested parentheses, that can help to guide you as to which one to do. And if you say it in the way I'm saying it, g of f of x. And remember, of means open a set of parentheses. G of f of 5. Working with the numbers is easier than working with the x's. Sometimes you must work with the x, like we did in the first example where we had f of g of x. Same two functions. Let's look at what the difference is if we do g of f or f of g with the same two functions. G of f means g of f of x. Well, f of x is the square root of x minus 4, so I'm going to take this and substitute it in here, and so g of f of x is that expression. You just substitute it in. That's all we can do. We can't do any simplification. There's no common factors or anything, so we just leave it at that. F of g of x we found previously was this. We did that on the previous example. Compare the two. Obviously not the same thing. And that's generally going to be true. When you're doing composition, if you do the functions in different order, you get different results. We're going to, later we'll look at inverse functions. Inverse functions are the only two functions where you get the same thing when you, no matter what order you do them in. But in general, two functions will not give you the same result if you change the order for the composition. this is the general rule. F of g of x is not equal to g of f of x. That's why it's critical that you perform the operations in the proper sequence. Okay, so here are two functions. What would g of f of 3 be? Remember, this means that means that. What is that equal to? I don't think this is up there, but what would this be? Same two functions. I don't know the answer because it's not on my slides. So I'm gonna... -3. Well, and that's why I suggest rewriting it each way. This time, each time you do it, put the nested parentheses. That'll help keep it straight. If you read it this way, then if you write it this way, this helps remind you work inside out. That can maybe help you with that order. You can even compose a function with itself. This says to do this. What's g of -2? It's minus a -2 plus 3 equals 5. So that means I need g of 5. Signs. That's usually the place that the error is in signs. Yeah. And, well, I've said it, and I'll keep saying it, watch those signs. They're little things, but they make big differences in the answer. And in the way we're working the problems with both the homework and the tests, it's either right or wrong. So it's either full credit or no credit, and the sign can make the difference between full credit and no credit. So be careful with those signs. Take your time, maybe work it, then go back and check it before you proceed, because it's easy to miss a sign like that.